Hello everybody and welcome back to Complex Analysis. Just a quick review from last time that I want to make so that I can have something to build this lecture on. A complex number is a number of the form z, where z is the complex number. Z equals x plus yi, where x and y are real numbers, and I is the square root of -1. A complex number, z equals x plus yi, can be represented as a point in the xy plane, as so. And I've said the xy plane, but when we're talking about complex numbers, sometimes we call this the complex plane. But when we're working with complex numbers, we call the xy plane the complex plane. And the x-coordinate of a complex number z is the real part of z. The y-coordinate of a complex number z is the imaginary part of z. Now I said this because I want to make a comment about complex numbers that I didn't make last time. It's probably obvious, but I want to make sure that I make the comment anyway, just so that I don't leave anything unsaid that needs to be said. And here's the point that I wanted to make. It would probably be obvious to all of you, but I just want to make sure that I say it so that we don't say, well, he never actually told us that this is true. It seems like it should be true, but he never actually told us that this was the case. I'm going to say it right now. And here's the point. Just as 2 points in the xy plane, x1, y1, and x2, y2, are equal exactly when x1 equals x2 and y1 equals y2. In other words, 2 points in the xy plane are equal exactly when the x-coordinates are equal and the y-coordinates are equal. It's also true that two complex numbers, z1 equals x1 plus y1i, and z2 equals x2 plus y2i, are equal exactly when x1 equals, oh my goodness, x1 equals x2 and y1 equals y2. Yes, two complex numbers, z1 equals x1, y1, I, and z2 equals x2, y2i are equal exactly when x1 equals x2 and y1 equals y2. So two complex numbers are equal when their real parts and their imaginary parts are equal. So when the real part of Z1 equals the real part of Z2, and when the imaginary part of Z1 equals the imaginary part of Z2. Now, this seems obvious, but I didn't want you to hesitate to assume that it was true because I didn't actually say that it was true. So this is the case with the representation of complex numbers in the xy plane or in the complex plane. Okay, next we're going to talk about the polar representation of a complex number. And the first thing we'll acknowledge is that the representation of the complex number z equals x plus yi in polar form is analogous to the representation of the point or ordered pair xy in polar form. Remember in Calculus 2 or Calculus 3, we did polar coordinates where we had a function of two variables, x and y. And we could represent that function in rectangular form, but we could also represent it in polar form. We're going to do exactly the same thing with complex numbers. The complex number z equals yi can be represented in polar form as z equals r, a magnitude, times cosine theta plus I sine theta, or just r and theta. And we'll get to the actual graphic depiction of that point in a second. Here's the point z equals x plus iy, or x plus yi, in the xy plane. It's this point right here. This point can also be represented in polar form as r times cosine of theta plus I sine of theta. And r is the distance of this point from the origin. But wait a minute. Didn't we say that the distance of a complex number from the origin was its modulus, absolute value of z, so to speak? So r is the distance of this complex number from the origin. And r is indeed equal to the modulus of z. I don't want to put too much up here at one time. So that's the significance of r. These things are functions of an angle theta, and theta is the angle that this ray makes with the positive x-axis. So that's theta. Now let's pause. I'm going to draw this picture all over again. And we're going to make some notes about r, theta, x, and y, and how we can express one set of coordinates, rectangular, in terms of the other, polar, and vice versa. Whoops. Okay, I guess I haven't changed this diagram too much. The first observation is that r is the modulus of z. And I guess we should tie Pythagorean's theorem in with this. Here is x. Really? No, I don't think so. Here is y. And here is x. And I left a space here deliberately. In terms of right triangle trig, y is the side of the triangle that is opposite the angle theta. And so y is going to be the hypotenuse of the right triangle times the sine of theta. Well, the hypotenuse of the triangle is r, or the modulus. So y, the opposite side, is going to be the hypotenuse, which is r, times the sine of theta. In keeping with our right triangle trig analysis, this side of the right triangle, that has length x, is equal to the hypotenuse of the right triangle times the cosine of theta, or r times the cosine of theta. So, given the polar representation, of a complex number, namely z equals r times parentheses r cosine of theta plus I sine theta, z equals r times parentheses cosine of theta plus I sine of theta. X is r cosine of theta, y is r sine of theta. And given the rectangular representation, z equals x plus yi, r is the modulus of z, the square root of x squared plus y squared. And how do we get theta? Well, to do that, I'm going to draw another picture. Okay, back with a fresh new blackboard or whiteboard. And again, we have the right triangle depiction with the imaginary part of the complex number being equal to r sine theta, and the real part of the complex number, x, being r cosine of theta. But in the context of a right triangle, where theta is the angle of reference, y is the opposite side, x is the adjacent side. So we can say that the tangent of this angle theta is the opposite over the adjacent, y over x. Well, if that's the case, then theta would have to be the inverse tangent of y over x. But we just apply the inverse tangent to both sides to get theta. And this works for what values of theta? Really, the inverse tangent gives us angles between what and what? Oh my goodness. But we got to go back to Cal 2 or Cal 3 to figure this out. And it probably wasn't emphasized that much in Cal 2 or Cal 3. But the arctangent function gives us values between negative pi over 2 and pi over 2. So in other words, quadrants 4 and quadrants 1. So if our number, our imaginary number, no, our complex number, if our complex number z equals x plus yi is in quadrant 1 or quadrant 4, this works. What if we have a complex number over here in quadrant 2 or over here in quadrant 3? Well, let's see. If we have a complex number over here in quadrant 2, the real part is going to be negative. X is going to be negative. The imaginary part, y, is going to be positive. So the tangent of theta is going to be a positive number divided by a negative number. In other words, tangent of theta is going to be negative. Just like if we had x, y in quadrant 4, the tangent would be negative because the real part x is positive, but the imaginary part y is negative. So if we have a complex number, x plus yi, in the second quadrant, the tangent is going to be negative. And the arctangent function of a negative number is going to give us an angle in quadrant 4. Let's draw out what that looks like. Let's draw out what that looks like. And let me be a little bit let me look into the future just a little bit with some insight. So I'll call this x1 and that y1. Here's theta 1. Now, let me go exactly the same distance to the left of the origin. And let me go the same distance above the origin. Oh, son of a gun, we get the same line. Son of a gun. This distance is pi. Now, is that relevant or not? Let's see. Might be. The magnitudes of the x and y coordinates are the same. x2 is just the negative of x1, and y2 is just the negative of y1. See, x2 is just negative x1, or x1 is negative x2, and y1 is negative y2, well, we square a negative number, we get something positive. So the modulus of this point R1 theta 1 is equal to the modulus of this point R2 theta 2. So the magnitudes or moduli are the same. Now the angles certainly aren't. This is theta 1 and this is theta 2. They're definitely not the same. What's the difference? Well, let's see. How do we get to theta 2? We can go angularly a distance of theta 1 and then go pi units. So we could say that theta 2 is going to be theta 1 plus pi. Okay. The tangent of theta 1 equals x1 over y1. But now x1 is equal to negative x2 and y1 is equal to negative y2. The negative signs cancel out. Huh. Okay. So where does this leave us? These two numbers are equal. So when we plug equal numbers into the arctangent function, we have to get the same thing. We're not going to get theta 2 here. for both of these, we're going to get a value between negative pi over 2 and pi over 2. This will correctly give us theta 1. Unfortunately, this is going to give us theta 1 too. So if we have a point in quadrant 2, and we try to compute theta using the arctangent, we're not going to get the correct angle. Instead of giving us an angle in quadrant 2, it's going to give us an angle in quadrant 1. So how on earth are we going to find the angle of a complex number in polar form if that complex number is a number that's in quadrant 2? Well, now that we see what's going on, it's not a problem, just as long as we're alert to the fact that if we take the x and y coordinates of this point and compute the tangent and then compute the arctangent of that, we're not going to get the correct angle. What we are going to get is an angle that is pi units away in quadrant 4. So we look at this relationship. Theta 2 is theta 1 plus pi. Oh, okay. So I guess we just had a revelation. If our complex number is in the second quadrant, we can get the angle of that point in polar form by computing the arctangent of y over x and then realizing this isn't really going to be the right angle. We need to add pi to this number to get the right angle, or the correct angle. So if we have a complex number in quadrant 2, just compute the arctangent of y over x and add pi. And I will say something about a complex number in quadrant 3. We're going to have a similar problem if we have a complex number in quadrant 3. And we're going to end up doing the same thing to get the correct angle. So instead of going through all of this again, If we have a complex number in quadrant 3, theta is the arctangent of y over x plus pi. Now, let's do it like this. This holds true if z is in quadrant 1 or 4. Okay. Those are our rectangular to polar conversions. And we'll just be aware that the arctangent only gives us the correct angle if z is in quadrants 1 and 4. If z is in quadrants 2 or 3, that is to the left side of the origin, we have to add pi to the argument. And now let's see. Polar to rectangular. Okay, that was simple. We should know the conversions both ways. Polar to rectangular, rectangular to polar. Why do we have two forms of representation? We're used to working in the XY plane. Why can't we just keep everything in rectangular form? Or why don't we just do everything in polar form and just stick with one or the other? And the answer is some algebraic manipulations are very easy to do in rectangular coordinates, but very difficult to do in polar coordinates. Okay, so why don't we just do everything in rectangular coordinates? We've seen that adding two complex numbers in rectangular coordinates is pretty easy. Just add the real parts and the imaginary parts and you got it. Surely that would be a complicated task in polar coordinates. And it doesn't seem that multiplication of complex numbers in rectangular coordinates is that complicated. Well, I'll tell you what, it can be complicated. Adding complex numbers in polar form, not too easy. Very easy in rectangular form. Multiplying complex numbers in rectangular form, not that easy. And let's see, exponentiation, isn't that just multiplication over and over and over again, like raising something to the 10th power? We're just multiplying it 10 times by itself. Well, you know, if we had to do that in rectangular form, that would be a pain in a place that I can't mention. But you know what? In polar form, it's very, very easy. Multiplication and exponentiation in polar form are easy, as are taking nth roots. How do you take the square root of a complex number? How do you compute the cube root of a complex number in rectangular form? I'm not sure. In polar form, it's really easy. So not just multiplication and exponentiation using positive whole number exponents, but exponentiation using fractional exponents is pretty easy in polar form. So we have rectangular coordinates or rectangular representation and polar representation because they each have distinct advantages over the other. And we're going to see some of the advantages of polar representation right now.